Welcome, Chem 222 cadets. This is Lesson 38, High Performance Liquid Chromatography, Part 2, in which we consider the impacts of mobile phase selection. Today, Lesson 38 brings your deadline for Results Report 8, the HPLC analysis of vanquish tablets. So if you have not done so already, please upload your document to Teams. Today we're going to continue our exploration of the parameters that we have to select to carry out a successful separation using high-performance liquid chromatography. In Lesson 37, we covered extensively the options and choices we have to make in regard to the silica support and the stationary phase that we're going to use. And now we're going to shift our attention to the mobile phase. The big advantage to gas chromatography as opposed to liquid chromatography is in regard to the mobile phase. With gas chromatography, we simply choose an inert gas, of which we usually do helium or some inert gas such as that. When we do LC, there is a much broader variety of mobile phases that we need to consider in terms of their relative polarity, and we will get into the details of this later. So it is primarily in the need to choose mobile phase and the complications therein that makes GC advantageous to LC. But once again, we really can't do gas chromatography on a lot of biomolecules that degrade at high temperatures, so we have no choice. We have to do LC. The other consideration with regard to the two techniques and compared to one another is the waste that does get generated when we do liquid chromatography. Because as a mobile phase, we are using solvents, typically organic solvents. Once we run many separations, there's considerable waste that's generated with those organic solvents. So one has to consider, is it feasible and possible to reuse those solvents? And if not, then we have to dispose of them through appropriate means. So there could be additional cost involved in the handling of the hazardous waste that does get generated when we do LC. To begin consideration of our mobile phase selection, just want to review some basics of the phenomenon that occurs as our mobile phase is going to pick up our sample and sweep it onto the top of the column, where we introduce the two different chemical environments. Any components in my sample are going to be exposed to this stationary phase material down here in the blue layer. Okay, and keep in mind your sample and its components within, we're going to have it in some kind of solution form, and so there is some solvent that we have to select in preparing our sample to inject onto the column. All right, so the separation occurs as our little blue triangle analyte species in our sample exposed to the mobile phase. If it's more like the stationary phase, it's going to partition into the stationary phase and hang out in the stationary phase for some time. Okay, in selecting our mobile phase, it's important that we tweak the polarity of the mobile phase, because we do not want our sample components to stay in the stationary phase forever. At some point, we want our sample components to come back out. At some stage in the separation, I need for it to finish traversing the column, come off the end, so it can be detected. So it's a delicate little balance in the relative polarity of the mobile phase and the stationary phase. And we will talk about how to approach that selection in the slides that come. So a couple thoughts on all of this. As we mentioned, the mobile phase typically is some combination of organic solvents that generates waste. They cost money. So when we do our separations, we always want to optimize the separations so that they occur in the most efficient time frame possible and utilizing the least amount of mobile phase. So practical considerations. So once again, in selecting our mobile phase, we need to take into account and be able to tweak the polarity so we get the ideal time spent in the stationary phase to affect the separation, but not let the molecules hang out so long that we're wasting a lot of mobile phase material. A second consideration is this solvent that we're dissolving our sample in. That is important as well. We're looking to the right at 2 chromatograms. This is for the separation of N-butyl aniline. Okay, and if we had dissolved our sample in methanol when we were using as a mobile phase solvent a 90-10 mixture of water acetonitrile, notice that this peak that we get off the end of the column is not ideal. It's broad and we have some tailing happening. So methanol is considered a fairly strong, what we call eluent in terms of polarity. And if we want to improve the peak shape of our analyte coming off, had we dissolved it in the mobile phase that I'm using, the 90-10 mixture of water acetonitrile, I get a much better looking peak that is very narrow and symmetrical. So in selecting our mobile phase, we want to use a polarity that's going to affect a clean separation in the least amount of time possible. And we also need to be cognizant of the solvent we're using to dissolve our sample. When we select a mobile phase for our separation, there are 2 very important considerations we must keep in mind. The first is a property known as eluent strength. Eluent strength is a measure of that solvent to pull something off of a bare silica surface, and remember the bare silica surface is very polar. Okay, so the measure of eluent strength of a solvent as a mobile phase, okay, is numerically related to this series in which we define the eluent strength of pentane, a very nonpolar species, which is going to have a weak ability to pull something off of that surface. It is defined as 0, and everything else is relative to that. So methanol with its OH group has the greatest eluent strength in the series, and these other solvents are somewhere in between. So in normal phase, where the stationary phase is more polar than the mobile phase, increasing polarity is increasing eluent strength. If we're doing reverse phase, decreasing polarity, so smaller values are going to increase eluent strength. So that's the first important thing to keep in mind. The other important thing to keep in mind when we select a solvent or a combination of solvents for a mobile phase is how we're going to detect things when they come off the end of the column. So at the end of the column, okay, you're going to have your analyte species coming through, but it's dissolved in the mobile phase, whatever solvent that is. Okay, so we got to know when our analytes are coming off the end of the column. We oftentimes use an ultraviolet absorption spectrophotometer as our detector. And so we want to make sure that we are going to get an absorption signal that is indicative of our analyte and not the mobile phase. So we need to know these cutoff nanometers where these different solvents quit absorbing in the ultraviolet. So That is an important parameter if we are using a UV detector so that we get a signal that is indicative of this species but not the mobile phase. To the right is a depiction of the layers that form between our stationary phase and our mobile phase in the bulk solution. Okay, we are looking at stationary phases of C18 in both cases here. So those are very nonpolar stationary phases. Silica surface down here. And the little black squiggly lines are our C18 molecules attached to the silica surface. So here's the depth of your stationary phase layer. Okay, if we had used methanol and a mixture of methanol and water as our mobile phase, we find that the layer of the methanol adjacent to my stationary phase is pretty small. This is what we call a monolayer. It's one molecule thick. Had our solvent and mobile phase been acetonitrile instead, notice that the depth of this layer that forms adjacent to my stationary phase is much deeper. Okay, it is the partitioning of our solute molecules into and out of both the layer of the mobile phase and into the stationary phase that's going to affect our peak shape as well as how long it takes for our solute molecules to come off the end of the column. So selection of the mobile phase is very important in terms of our detection mode as well as the time it's going to take for a separation and the shape of the peaks that come out at the end. When we carry out a separation, we have to choose the nature of the solvents we're using in the mobile phase. Are we going to use the exact same mobile phase components in the exact same proportions throughout the entire separation or not? If everything remains constant throughout the entire separation, that is called isocratic elution. Depicted here are a series of chromatograms for the isocratic elution of a particular sample as denoted in the figure caption. And we are going to vary the combination of our mobile phase depicted as a combination of two solvents, A and B. Okay, so let's begin looking at what our chromatogram looks like if I carry out my separation isocratically, in which my mobile phase is 40% B and 60% A. Okay, so we have two components in our mobile phase, and if I carry it out at the constant composition of 40-60, this is the resultant chromatogram. Okay, as far as resolution is concerned, I do not have good resolution between peaks 2 and 3. Okay, but I do get pretty good resolution for the remainder of components 4 all the way down through component number 8. Okay, and notice the time of my separation. Oh, it's taking me over an hour to do this separation. If I change the composition of my mobile phase to be 30% B, 70% A, notice that I get really good resolution now for peaks 2 and 3. Okay, and that happens within the first 10 minutes, and it's taking longer for the rest of the components to come off the end of the column. If I change my mixture to 35% B and 65% A, okay, once again, I'm getting really good separation of components 1 through 3. They're coming off quickly in time, and I still have resolution. I still have baseline resolution, so that's optimal. But Notice what's happened to the time it takes to get component B off. Now it's taking 125 minutes to get, component 8. My last component that comes off, it's taking me a really long time, over 2 hours to get that component off. All the while I'm wasting mobile phase and generating a lot of waste. So that's probably not an ideal scenario. Okay, other combinations are illustrated to the right here. So here's where we have 90% B. Okay, if I have 90% B, I'm not getting good resolution between 5, 6, and 7. Okay, at 80% B, okay, it is still not ideal. Here's 70% B. Here's 60% B. We're getting better. Okay, so notice that I'm getting my component 8 off in a much better time frame, maybe 12 minutes here. Okay, but I don't have resolution of peaks 2 and 3. And here's the scenario for 50% B, 50% A. Okay, 8 is coming off in 25 minutes, and I'm not getting resolution between 6 and 7. Okay, so isocratic elution is going to be problematic from the standpoint of getting a clean separation in a reasonable amount of time. So how can I get around this problem? Well, obviously, I get very good separation of my early components if I'm conducting the separation around 35% B, and I get good separation of my latter components if I'm running my separation at a higher percentage of B. So the solution is to not just run the separation at a constant composition of my mobile phase mixture, but have the capacity to change that over time. Because we are using an instrument that is interfaced with a computer, we can program the computer to tell the instrument to mix my solvents at different proportions at different times during the separation. This is known as gradient elution. So this way I can tweak the composition of my mobile phase and its relative polarity as a function of time to get all of my components off with good resolution in the least amount of time possible. Had I conducted the separation depicted in the previous slide using gradient elution, okay, to get my early components off cleanly, I want to use 30% acetonitrile. Okay, that gets these components 1 through 3 off in less than 10 minutes with good resolution. Okay, to encourage the rest of my components to come off in a faster timeline, I'm going to increase the composition of my mobile phase up to 45% acetonitrile between these minutes, so like from 13 to 28-ish minutes. Okay, by increasing the composition of the acetonitrile, I'm successfully getting off components 4 through 6 with good resolution. And then finally, to get peaks 7 and 8 off, I need to ramp up my composition to 80% acetonitrile. And in doing so, now I get peaks 7 and 8 off with good clean resolution, baseline resolution, and good peak shape. And the critical thing, look at how long it took me to complete the separation. I'm getting my separation done in about 37, 38 minutes, as opposed to the isocratic elution, which required 120 minutes to get peak 8 off. So gradient elution is a very powerful tool that is used in liquid chromatography to tweak the eluent strength of the separation as a function of time so that we get the best resolution in the least amount of time possible, generating the least amount of waste. As you likely have noticed by now, choosing the ideal parameters with which to carry out a particular separation of a specific sample and all the choices you have with regard to the stationary phase and then the mobile phase, this is a very complex process. So the process involved in identifying the most ideal parameters for a particular separation is called method development. It's a big part of research and development, as I described, as scientists are trying to find a cure for COVID. The analysis of samples, complex samples, involves this method development process. We have to choose the appropriate stationary phase and all of the parameters that go into that. And then we have to choose the appropriate mobile phase. So is there a systematic way that we can go about to hone in on what is this sweet spot of combination of organic solvents to use in the mobile phase that affects the best resolution in the shortest amount of time possible? So typically the way this is done is we have a computer at our aid, which is going to help us model the resultant chromatograms we're going to get with different combinations of mobile phases and eluent strength. So typically we will look at a mixture of 3 different solvents. This is acetonitrile, this is methanol, and this is tetrahydrofuran. Okay, so if we're going to use a combination of 3 solvents, we can collect a spectrum. We can collect a chromatogram in which we use this solvent and this solvent. Okay, and you can start with pure methanol, collect that chromatogram. That's this one. Pure acetonitrile is here. Pure tetrahydrofuran is there. A 50-50 mixture of these two is in between, and you do that in between. And then we can also collect a chromatogram and get data on our retention times and peak shapes when we do equal proportions of the 3. If you get that data into a computer, there are programs that can be run which are going to help you identify your most ideal combination of those 3 solvents, solvent A, B, and C, to affect, once again, the complete resolution of all your components in the least amount of time. So in summary, here is a list of all of the choices and selections one makes with regard to stationary phase material, the silica onto which the stationary phase is bound, the column, its dimensions, the flow rate, the mobile phase selection, the gradient, the temperature, sample considerations, and then at the end we have to choose a detector. Okay, the most sophisticated detector to interface to a chromatograph, a liquid chromatograph, is a mass spectrometer. And the operation of that mode of detection would then require a very detailed series of choices therein. So this slide is simply meant to remind you of the complex nature of carrying out an effective separation by LC. It's not impossible, but it certainly is not simple either. To complete our consideration of all possible options available to us, I just wanted to bring to your attention there are some other chromatographic methods at your disposal. So supercritical fluid chromatography, SFC as it is known, How it differs from the methods we've considered thus far. If you'll remember a phase diagram of any particular solvent, okay, you have the triple point where all three phases exist at the same time. Okay, this is where the melting curve interfaces the sublimation curve and the vaporization curve of a substance. So the vaporization curve of a substance, let me come back and do it in a different color. So here's the vaporization curve. It separates the liquid and the gaseous phase. If you're on the line, you're undergoing the process of vaporization. Okay, this curve actually has an endpoint. If you are at any temperature greater than that at the end of the vaporization curve, or you are at any pressure, if you're at any pressure greater than that here, or any temperature greater than here, that substance is what's known as the supercritical fluid. A supercritical fluid takes on odd solvent behavior. Sometimes we can exploit that for the purpose of chromatography. So if we place our mobile phase at a pressure and temperature such that it's a supercritical fluid, we might be able to use solvents other than organic solvents that are not as harmful to our environment, such as carbon dioxide. So supercritical fluid is another option of chromatography. And just also wanted to point out that we can exploit the chirality of analyte species in a separation by using chiral columns, in which you've got an optically active center for the materials that are bonded to the silica surface. So these are other options and tools available to you for separations. Our final consideration are the instrumental components in a high-performance liquid chromatic graph. So here's a nice picture of an HPLC. Okay, at the top we have a solvent tray over here. So you see the bottles of different solvents that can be used in combination. Typically, there's usually 4 bottles available. As you've seen, oftentimes we like to combine 3 different solvents as our mobile phase, and the other bottle oftentimes is used for a buffer. Oftentimes it's important to also control the pH of our mobile phase as we conduct a separation. So there's your solvent tray at the top. It is important that we remove gases from our solvents before introducing them to the column, so there's usually a degasser. The solvents have to get pushed through the column under high pressures, so we have to have a pump. We have to introduce our sample somehow, so there is a sample tray. Typically, we have an auto sampler where we can load up a number of vials, and the instrument will be programmed to analyze samples one right after another. If we wish to control the temperature of our column, we're going to have a thermostat. Okay. Then we are going to have our analytical column. Okay, and prior to the analytical column, we're going to have a guard column and plumbing that obviously pushes the mobile phase onto the head of the column. And once components come off the end of the column, then they're going to have to be connected down to some form of a detector. In this case, it's a UV absorption, UV visible absorption spectrophotometer that has a diode array detector. Depicted down below is an actual column in its metal sleeve. Okay. All right, and once again, that is the heart of the column where the actual separation takes place. This slide is a schematic diagram of the components within our HPLC instrument. As I mentioned, we have a number of bottles that contain the various solvents we're going to use in our mobile phase and potentially a buffer solution. Okay. Once again, it's critical that we have a degasser to remove gas from each and every one of these solvents. Gas bubbles are going to disturb the packing in our column and ruin it, which is disastrous, so we can't let that happen. We have to have a mixing valve, which is going to give us the correct composition of my solvents A, B, and C as under control of the computer. It's going to tell me what combination of solvents to use at that particular point in time. Okay, that mixture of solvents, okay, is going to have to be mixed. And then this entire system is called the gradient system. And then we have to have our pump, which is going to apply the high pressure and push that solvent down through an equilibration coil. Okay, we don't want it to have a pulsating flow, so we want that to come out smooth, the pressure to be consistent. We have to protect our expensive column, so we always have a guard column to trap any solid particulates or any other materials that are too big to go onto our column. Okay, and then we have a split valve, which will allow for some of the solvent to go to waste depending on flow rate. And the next item is our sample, and we have to introduce the sample. We do so with what's known as an injection port. Okay, with an auto sampler, there's a syringe that sits on top and a rubber septum will be penetrated and it will drop the appropriate amount of sample and introduce it into the injection port. Okay, from there, the mobile phase sweeps the sample onto the head of the analytical column. So here's the heart of our separation. Our analytical column, separation occurs. Okay, and if we wish to control the temperature of our separation, all of these components in the dotted line, we will regulate the temperature within there. As components come off the end of the column, okay, we need to direct them into some form of a detector. Okay, there are several types of detectors we can use. When you purchase an HPLC chromatograph, it's like buying a car. You have all kinds of options. You can have a UV visible detector, fluorescence detector, refractive index, evaporative light scattering, electrochemical. It is a plethora of options in the means of detection. Or something as sophisticated as a mass spectrometer. Okay, price just went way up. Obviously, everything is under computer control, including the proportional mixture of the mobile phase, etc. We record our data and we store it. I forgot to mention back up here, vacuum pumps that are used to drive our pumping system. This slide is an illustration of the pumps and valves typically found in an HPLC instrument. When it comes to our pumps, okay, remember we must have an appropriate pressure to get flow over our packed bed of stationary phase particles. So depending on the size of those particles, that dictates the pressures that must be used. If we're dealing with tiny particles, less than 5 microns, we likely need ultra high pressure pumps as opposed to traditional pumps. So that must be taken into consideration when selecting an instrument and its components. Pumps typically come as reciprocating or displacement. The thing to consider is that as the pump pushes the mobile phase, okay, it can generate a pulse, which is not going to be a desirable feature when we get to detecting our species as they're coming off the end of the column. So you want to dampen any pulsating flow. So in the design of the pumps, okay, you have a lot of pistons, and oftentimes you're going to find a damper to remove that pulsation. The other component that works hand in hand with your pump is the combination of solvents that we need to draw from each of the bottles. And that's under computer control to tell us what the appropriate proportion is at that point in time. And so we have what is known as a proportioning valve that's going to draw solutions out of each of our solvent bottles in that appropriate combination is going to get mixed and then pass through the pump so that it can go on and pick up our sample and carry it onto the column. The component in our instrument that allows us to introduce our sample is known as an injection loop. The injection loop is going to ensure that we introduce a very fixed and reproducible volume of our sample onto the column. We are going to use a microsyringe to draw up a certain volume in microliters. This can be done manually, or if we have an auto sampler, we have a series of vials at precise positions. The computer positions the instrument to a certain vial. Microsyringe through automated control extracts through a rubber septum in the top of the vial a certain volume, which is typically in excess. Okay, the first step is to load the sample loop. So we inject our sample. Okay, we have a precise little plug of our sample right there, and the excess gets pushed out and into waste. Okay, so now I've got this little plug of my sample ready to be swept onto the head of the column. So then I position the loop into the inject position. So now I get mobile phase solvent flowing in. It comes through here. It carries my little plug of sample that I loaded into the loop right there onto the head of the column. Once the sample separation has occurred in the analytical column, I should have individual components coming off with respect to time. Okay, so I need to have some means of detection that's going to give me some form of an analytical signal as a function of time as different components come off the end of the column. So the options available to me in terms of detection, I can have an ultraviolet, a UV visible absorption spectrophotometer. Okay. I can have a refractive index detector. All species has a refractive index and will give rise to a signal. I can use an evaporative light scattering detector, charged aerosol. There are electrochemical detectors, fluorescence. Okay, you can have a combustion detector. So if you have combustible species, you can use that as an analytical signal. There are conductivity detectors. Anything that has a charge is going to conduct electricity. Or you can actually interface a liquid chromatograph to either a mass spectrometer or an FTIR, a Fourier transform infrared spectrometer. So considerations as to choice of detectors. Obviously, Limits of detection are critical, and here are the considerations with regard to that. We also have the consideration of whether or not these detectors can be used with a gradient, changing mobile phase composition. So that might dictate which detector is going to be appropriate for a certain separation. Shown in this slide is the flow cell that we use in order to collect a spectrum if we are using either a UV visible absorption detector or a fluorescence detector. So we have components coming off the end of the column, okay, and they are going to enter what we call a flow cell. So solution comes down. Okay, I have my analyte species of interest that has been separated, and it is in the mobile phase solvent, whatever that is at this stage. All right, so if it is a UV visible absorption spectrometer, we have to have a UV lamp and or a visible lamp at this stage. Typically, we are going to have a diode array detector so that we don't need a monochromator to select a specific wavelength. Light will pass through an optical window, be focused into our sample, which now is going to occupy this volume in the flow cell. So there is that defined path length for Beer's law. Absorbance is extinction coefficient, path length, concentration of the species within. Okay, and this is a real-time device. So obviously, as a function of time, we're going to monitor certain wavelengths, and using the grading, diffraction grading, we can detect the intensity of light coming from different wavelengths all at the same time, and we can monitor one specific wavelength. In this case, this is actually a fluorescence detector in which we select both the excitation and the emission wavelength. But in the emission wavelength, as a function of time, we can easily see that one component comes off here at 2 minutes, something around 5, and then something a little shy of 6. This slide includes a schematic illustration of an ultraviolet diode array detector. Okay, if we're going to measure the absorbance of ultraviolet radiation, we need a deuterium lamp, as we've discussed previously. Okay, radiation from that lamp is going to be focused on mirrors. It's going to strike a beam splitter. The purpose of a beam splitter is to split out the light into two optical paths. Okay, so one of those paths, my beams of light are going to bounce off mirrors and eventually be focused through the sample aperture and flow cell. The other half of the beam, once it strikes the beam splitter, is going to pass down here through a reference aperture. Okay, so half the light's going to pass through my sample, the other half will not, and so I can compare the intensity of the light at a particular wavelength coming from those two paths. Okay, and then the two beams are going to be recombined so that I get light coming in here, recombined, focused on eventually my, this is my diffraction grading here. The grading here is going to split the light into all kinds of different wavelengths, and the angle at which they come off will be detected using my photodiode array, which is capable of measuring the intensity of light at different wavelengths as it strikes the photodiode array detectors all along the two-dimensional positioning of that detector. So once again, we're able to, the computer is able to say, hey, I want to follow the absorbance at a particular wavelength as a function of time as components come off the end of my column. And so indeed, you know, you're going to see different things coming off at different points in time at that particular wavelength. Another option for detection to interface with a liquid chromatograph is an electrochemical detector. So all of the wonderful methods that we learned about electrochemistry can be exploited for use in detection of the components coming off the end of the column. Okay, so once again, the solution of our analyte species and the mobile phase are going to populate a flow cell. Okay, and here's our reference electrode, our potentiostat, our working electrode. Okay, so we can actually measure potential of the solution coming off the end of the column and onto waste. So we can exploit those methods of analysis as a means of detection. Another option of detection is an evaporative light scattering detector, an ELS. Oftentimes when we're doing LC, we want a detector that's going to respond to any analyte as it comes off the end of the column. This is one of those. And so it has some advantages in being a general purpose responding detector, and other key advantages in terms of its sensitivity greater than a refractive index detector, which is also a general purpose detector. A refractive index detector is a general purpose detector that will give me a signal for anything that comes off the end of the column. Okay, all species, all solutions are going to have a refractive index, and the way these work is you have sample coming in, populating the chamber, you have a light source, okay, and we are going to have any light coming out, following through a deflection plate to a photodiode array detection means. And so once again, this is a general purpose detector. It typically has the least sensitivity detection limits. So okay if you've got fairly high concentrations of your species coming through. To end our discussion of high performance liquid chromatographs as instruments, the most powerful thing we can do with a sample separation device is interface it with a detector that is actually one of our methods of structural elucidation. A mass spectrometer is able to give us a full spectrum for any component coming off the end of the column, in which we're going to be able to search against a library of spectra and identify the exact structure of the compound coming off the end of the column. That's a powerful combination. Shown to the left here is a nice illustration of an LCMS, in which obviously you've got your high performance liquid chromatograph, and as the components come off the end of the column, they are going to enter into a mass spectrometer. So components on the left are the LC, and then to the right, we're entering into a chemical ionization interface, which is how we introduce a sample into the mass spectrometer. And the resultant spectra that we get, the top, here's our chromatogram. So this just shows as a function of time, we have different components coming off with different retention times. Okay, and so in addition to just knowing that something came off at a particular point in time, I can come back and say, oh, the peak at retention time 4.67 minutes, so somewhere in here. Okay, I have a full mass spectrum of that component. Here it is. I can run this spectrum against a library of known compounds, and I could identify, oh, this is the structure of the compound coming off at that point in time. So this is incredibly powerful. As you might anticipate, these instruments are the most expensive. An LCMS is going to cost you well over $100,000. And the greater the capability of the instrument, the more expensive it's going to be. I would like to just state that in order to make these kinds of instruments a possibility, there's a delicate research and design phase that has to happen with the interface between the components that are coming off the end of the column and how they enter into the spectrophotometer. But once all of the kinks were worked out with regard to that interface, these instruments became commercially available, and they are extremely powerful. So this ends our section on high-performance liquid chromatography, and we will give consideration to gas chromatography next and its advantages in application as opposed to LC. Thank you very much for listening.